Hello everyone, welcome to aplusbi. This channel is all about complex numbers, and in this video we're going to be solving a nice equation with complex numbers. It's a nice equation because it contains pretty much everything. We have the z, we have the complex conjugate of z, and the absolute value, or the modulus, right? So it's kind of like a mixed equation. If you're new to complex numbers, go ahead and check out my lecture videos. I made 9 videos on basics of complex numbers. But let me just tell you, any complex number can be written as a plus bi, where a and b are real numbers, and I is the square root of -1. I can also be written as I squared equals -1, because if I is the square root of -1, then you can square both sides. Make sense? So never ever forget that I squared is -1, because we always use that fact. Now this problem is kind of interesting because its solution involves, anyways, we'll talk about it, okay? Let me not spoil it for you. So how do you solve these kinds of equations? Well, what's the name of this channel? It's a quick quiz, a plus bi. That's what you use. So we're going to go ahead and replace z with a plus bi. But then we're going to switch to something else, and there's a good reason behind that, which I'll tell you a little bit later. But for now, let's go ahead and stick to a plus bi. Now, what is the complex conjugate of a complex number? The complex conjugate is a special number so that when you add to the original or when you multiply by the original, you always get a real answer. And that's unique in that sense, so that we can write it as a minus bi. Notice that when you add these two, you get a real number. When you multiply them, you get a real number. And also something special about the product is you get a squared plus b squared. By the way, the absolute value of z is square root of a squared plus b squared, which is by Pythagorean theorem. If you draw a graph plot on the complex plane, argon plane, you'll get that. But also there's a really strong relationship between these two things. Notice that if you square the absolute value, you get the product. So in other words, z times z bar is the absolute value of z squared. Make sense? Cool. And that obviously this idea kind of gave me a lot of problem ideas, but anyways, we'll talk about those later. So let's go ahead and plug these in. Z is a plus bi, and then the absolute value of z is the square root of a squared plus b squared, and the conjugate is a minus bi. The whole thing is equal to 13. Awesome. How do you solve something like this? Easy. We're going to set the real parts equal to real parts, and imaginary parts equal to imaginary parts. That's pretty much it, right? Easy. So let's go ahead and simplify this a little bit. Bi cancels out, which is nice. Remember what we said about complex conjugates. You get a real answer. A plus a is 2a, and then square root of a squared plus b squared, and that's equal to 13. Uh-oh, what happened to the imaginary part? It disappeared on both sides, so that's nice. We don't have to worry about it because imaginary parts are 0. Well, you should have known because there's nothing imaginary on the right-hand side, right? So if you had some imaginary part on the left, it will be 0. Make sense? Okay, hopefully. Now, where do you go from here? Well, you can try to get rid of the radical, right? But before we do that, I want to make a switch. And you know why? Because if you look at this carefully, you can realize that there's only one equation, but we have two variables. Are we looking for integer solutions? Probably not. I don't know if there are any integer solutions to this. Maybe there are, and we can test it out. For example, if a is equal to, let's see. First of all, 2a is always even, so the square root of a squared plus b squared must be even, which probably means b is even as well, right? So let's see. What happens if a is 1? Then this is not going to be even. Oh, this is odd, right? So this needs to be odd. And because of that, b needs to be odd, I think. Can a be odd? Let's see. If a is 1, then we're going to get 11. And then this is going to be 121. And if a is 1, b is going to be square root of 120. It's not an integer. Anyways, we can keep trying this. I don't know if we're going to find any integer solutions. I doubt it, but there might be 1 or 2. You can try a equals 2, and that'll give you, basically you can subtract this. So you can do the following. Like if a is equal to 2, this is going to be a 9. then this will be an 81. If a is 2, this will be 4, this will be 77. It's not going to work. Anyways, you can test it out, see if there are any integer solutions. I'm not going to worry about that because I need to show you something else. So we're going to go ahead and make a variable change. I'm going to replace a with x and b with y. Instead of a plus bi, I'm going to use x plus yi. Why? You might be questioning. Because this equation is single, there are infinitely many solutions. In other words, this is a locus problem, right? I didn't tell you that ahead of time because I didn't want to spoil the surprise. But yes, if you do the replacement, you're going to get 2x plus the square root of x squared plus y squared equals 13. Let's go ahead and work with this. Subtract 2x from both sides. And the next thing we do is squaring both sides, right? Obviously. We want to get rid of all the radicals. X squared plus y squared equals 169 plus 4x squared minus 52x if you do the formula. And then I'd like to isolate y squared, maybe for now. And then subtract x squared. And then you're going to get something like this. What type of equation do we have, right? I mean, you can kind of split it up into two cases if you want. You don't have to. But one of them is going to be like this. And the other one is going to be the opposite. Or you can put a plus minus sign. What does this give you? Kind of like a linear? Not really, because it's the square root of... So there's something radical about this. Could it be one of the conics? I'll show you a graph at the end, which will give you an idea about what this equation looks like. But we can definitely do something like this. You can write this as... Let's just leave the 169 outside. And we can kind of take the 3 out. And then kind of complete the square. You can add half of this squared, which is 26 over 3 squared. I don't know. That's going to be a number. But basically, the whole idea is we can write this as 3 times x minus a squared plus b. And then from here, what do you get? You can put both of these on the same side. But notice that y squared and x squared have different signs. They're not the same. If they were the same, but their coefficients were different, there will be an ellipse, right? If they had the same coefficient and they were both positive, and of course you had a positive number on the right-hand side, then what happened to my b? Just erased. Okay. Then you would have a circle. So what is this? Okay, we'll get to that in a little bit when I show you the graph, but that's basically how you can express the solutions. Probably this is like a more general and nicer form because we're going to work with that. And here's the graph. Are you ready? Ta-da! The graph is, what does that look like to you? It is a hyperbola. Yes, that's what happens when you have an equation like that. In other words, all solutions, I meant to use a different color, all solutions to the equation that I gave you lie on this hyperbola. Hyperbola spelled with an A, right? Not with an E. That's hyperbole. That's a different word. Anyways, this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.